Hi, everyone. Thanks for joining me today. Today I'll be talking about CVE 2022-47929. Who here is familiar with what this is or what this means? Any takers? Just one? Really? Okay, that's fine. We're all here to learn tonight. So CVE stands for Common Vulnerability Exchange. So it's basically a database where you will register any vulnerabilities you find, and as they get fixed, any pertaining information to those vulnerabilities get applied or get set to that or added to that website, and they get assigned not only a number but also a score. In this case, today we'll be talking about noqueue, no problem. This was given a 5.5 out of 10, and we will learn why. Next slide. Oh. Okay, that didn't mean to happen. All right. So my name's Fred. I'm a systems engineer at Cloudflare. I used to be one of you. I'm a web developer, primarily a back-end web developer, very extensive PHP. I have a colleague who also used to do PHP. So if there's anyone here that does PHP, just so you know, PHP developers lead to kernel developers. I now write code for Linux kernel. And I also do. Make tools for various operating systems like Ubuntu, Debian, things of that nature, and I primarily work in security. So before we get started tonight, I have to go over some background information real quick about what noqueue, no problem actually is under the hood. So we'll just jump right into the story of that. It all started with a Jira ticket. In 2019, we had a network engineer create a ticket in Jira, essentially coming to us with a crash that was happening on one of our systems. They were testing various commands to manipulate network traffic, and it ultimately resulted in a crash. Nobody knew what to do at the time with that ticket, so it was backlogged. And then in 2022, I was hired. And in late 2022, I was assigned the ticket and ultimately fixed it. So we're going to learn about pointers tonight. So the crux of this vulnerability revolves around what is known as a null pointer dereference. So here I have some C code. If you were to type this into a file and actually compile it, it will work. Nothing more than that, pretty simple. But where I find like a lot of people misunderstand pointers and get confused by them is that there's really like 3 different ways you can use the asterisk there. One of which is to define a pointer type, dereferencing, and of course multiplication. So what is a null pointer dereference here? So when we think of a pointer, we create a type int star. So that is our pointer type. I'm giving it the variable p, and I'm assigning it to 0. So pointers point to addresses in memory. And when I do this return right here, I'm actually doing what's known as a dereference operation. So what I'm saying is, go to that memory address, give me back whatever's stored there, and cast it to an integer. In this case, nothing is going to happen because nothing is because we're trying to access memory at the position 0. And it results in something like this. We get a segmentation fault. We can use a tool called core dump cuddle. People will either say cuddle or CTL. I'm going to say cuddle because that's more fun. So when your program crashes, you're going to get what's called a segmentation fault. And a segmentation fault essentially just means that we're trying to access memory in an out of bounds location or in a restricted area. So in this case, 0, the address 0 is actually reserved and is considered outside of program memory for access. I could have easily just put -1 as the value and tried to dereference from that. Same thing. You can kind of think of these as index out of bound errors. But we can use a tool called core dump cuddle to actually launch a debugger to kind of see what happens here. So when you actually come across a null pointer dereference, you can run this tool on your Linux. Oh, by the way, we're talking about Linux tonight. But when you install this program and run it, it will open up a GNU debugger, and from there it'll tell you exactly what went wrong and where, assuming you have debug symbols compiled into your program. And in this case, I do, and it tells us exactly what went wrong. So a segmentation fault is kind of like a very obscure error message. It doesn't tell us anything, which is why we kind of go into this debugger and see what's actually going on at line 4 of this null deref.c file. And if I type list, you can see the entire program there. But what about the kernel? The kernel is a little bit more interesting. So instead of blue screen of death, like you get on Windows, the Linux kernel will actually give you a lot of information that is very scary indeed. We're actually only going to focus on a little portion of this here. Typically, when you get a crash report like this, there are some key things to take a look at. So at the very top, it kind of tells you exactly what's going on with the crash. In this case, we have kernel null pointer dereference. The PF supervisor read access in kernel mode and the PF error code, blah, 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 not present in page, essentially means that we're trying to access memory in a bad spot, right? What's kind of funny here is that when we see stack traces like this, we do get a little bit more information. In this case, there is the RIP, RIP, and it actually tells you what crashed, like what function actually crashed inside the kernel. And it's surrounded by, in this case, brackets, which tells you which module crashed. So in order for me to produce this error message for this demonstration, I wrote a kernel module, loaded up to the kernel, crashed the kernel, and we get this. There's also some other useful information these things provide. I'm not going to go into everything because there's a lot here. Code is just the disassembly, or not really disassembly, the actual binary that where the fault actually occurred. And then you get also some like information of what actually caused the crash, where it says CPU 7 and PID 891, and then COM right there. So it says that insmod is the task in which this crashed, and then all the way to the right we have the actual kernel version that crashed. So there's like all this sort of information when we have a kernel crash that you can kind of lean off of to debug what's going on. Unlike say a user space program where we had to actually open up a debugger to figure out what's happening. Now comes the fun part. I have to say this. Do try this at home, but only on computers that you actually have explicit permission to do this to. We are actually going to create an exploit tonight, and we're going to run that exploit, and we're going to talk about how we actually mitigated this exploit. So fair warning, do try this at home. Just make sure you have permission to do so. So now I'm actually going to jump into the fun part of this presentation. So how can we use traffic control to cause a kernel panic? Well, first we have to understand really what the CVE is. So CVE-2022-47929, in the Linux kernel before 6.1.6, a null pointer dereference bug in the traffic control subsystem allows an unprivileged user to trigger a denial of service or system crash via crafted traffic control configuration that is set up with TC, QDisk, and TC class commands. This affects the QDisk graphed in NetSketch API. Now, we will go over what all this means here in a moment, but this is the actual description of the CVE. So if you Google this, this is what you will find. So let's kind of break this down a little bit. So let's talk about denial of service. So usually when you hear denial of service, a lot of people will tend to think of distributed denial of service. So we're talking many nodes or many computers, many devices, all sending packets to, say, your website to try to bombard it to take it offline in some capacity. What we're going to be talking about today is a traditional denial of service. If anyone remembers CrowdStrike recently, that was an unintentional denial of service attack that occurred earlier this month. Or was it July? Was it? Yeah. But the interesting thing about these two different distinctions is that, like, yeah, you could have a denial of service attack that could cause crashes and cause a severe degradation, but you can use services like Cloudflare, for instance, to actually mitigate these problems and hopefully your systems recover from this. Now, however, when it comes to a traditional denial of service attack, these things are arguably more complicated and harder to actually debug and find the root cause for. For instance, CrowdStrike, I mean, I'm pretty sure they knew exactly what happened the day of, but obviously they just gave the report this week. But these things are very hard to fix. A lot of people had to go into their systems, mess with secure boot, do all sorts of crazy stuff to try to recover from the damage. And that's exactly what we're going to try to do today. So what is traffic control? So this is a little bit more complicated. So at its very is very simplistic term, traffic control is just a subsystem in Linux. So that allows you to route packets throughout your system in and out and to various parts of the system. So you can have different queuing strategies. You can do packet filtering, all the bullet points on here, monitoring, all sorts of fun stuff. And then specifically, we're going to be talking about hierarchical and then traffic control disciplines, queuing disciplines, and then noqueue specifically. So essentially, all we need to know about traffic control is just that it moves packets around. But what is noqueue? So noqueue is a special kind of queuing discipline within traffic queue. That's primary purpose is to just be basically a no queuing queue discipline. So essentially, when packets come in, the kernel you have the choice to just immediately drop them or pass them on through, whatever works, right? That's basically what no queue is. Now traditionally you'd want to have a queue so you can actually do stuff with those packets. Queuing, you can fill buffers with them. You can pass them around, move them around, et cetera, but this is just send packet, send packet, send packet, send packet, or drop it if it doesn't fit. And you can get this information on your computer simply by typing IPA. IP is a tool that allows you to grab any information you want about your specific computer's interfaces, which could also be tied to your network devices on your computer. Or in this case, a loopback interface, which is simply a virtual interface. And we're going to use this to perform our exploit. So this is it. This is the exploit. I'm going to break it down because there is a lot going on here. So the first thing I do is I assign the variable dev equal lo. So in shell scripting, this is me just saying, I'm going to set this variable. I'm going to use it in all these other commands. It's pretty obvious just by looking at the code. Then what I do is I set up a link. So the device, if it's down, go ahead and bring it up. And in this case, the device is the interface, which is the loopback interface, which all computers have. And then I'm going to run the traffic control program, where I'm going to replace the queue discipline for the device with a hierarchical token bucket queuing discipline. I'm not going to go into details about what that means, but essentially it's just you can think of it as like a tree, and we're giving and then based off the conditions of different leaf nodes within that tree, it's going to pass packets around and move them around. In this case, the other commands are just to set up that one of the leaf nodes is going to be the noqueue traffic queuing discipline. And then finally, we go ahead and we issue a ping. The -i dev just means we're going to use this interface to perform the ping. W, I forget what that means, and then C, I forget what that means, but we're giving it we're going to try to ping the IP address to Cloudflare's 1.1.1.1. And then, of course, we're going to get rid of all the output because we don't care what the result of the ping is. But to the astute, you may have noticed, all those commands were run as root, right? So normally when we talk about Linux programs running as root, you might think, well, it's root, who cares, right? We cause a crash, who cares? We're running as root, who's going to get root? Privilege escalation, who cares? Whatever. But that's not what this is about. No. We're going to do this as a regular user. You don't need to be root to break this laptop. So in order to figure this out, how we're going to get essentially root access without being root, I first need to figure out where this program is located, because technically speaking, on Debian operating systems, anything that's within the user sbin folder is typically reserved for system level tooling. Usually you require root permissions to actually to run these tasks or these programs, but you can still run them because they have the execution bit set to basically anyone on the system can run these. But once you run them, they're not going to really do anything because, again, they still require root. But so I run the find command here to first figure out where this is. The hyphen executable, as the name implies, just means I'm going to search my entire root directory for any executable, for any ignoring case insensitive name of TC, and then anything that's permission denied, throw it out the door, and we get this result right here where we have user sbin TC. So what I'm going to do now that we found it out where this is located, we're actually going to now use a tool called capable. So essentially, what capable does is allows you to it's an eBPF program that allows you to actually monitor what permissions each tool you uses on your computer. Now, this tool doesn't come by default on your computers. You're going to have to install the libbpf tools in order to get it. But it's really handy because when I run the traffic control command, we can see right here on the right that we get a RT-netlink operation not permitted. That's just me. That's just the computer saying, "Hey, look, you're not root, so you're not permitted to perform this operation." But we can see that the output for the capable tells us exactly what we're missing. We are missing, in this case, the capability net admin. So how do we get that? We're going to leverage what's called namespaces. So typically when we think of containers, this is it. I know that a lot of you are very familiar with Docker, maybe Podman. At the core of it all, containers are essentially namespaces, and namespaces are containers. It's the technology that's fundamental for sandboxing your applications from the host operating system. So what we're going to be looking at specifically today is what's called the user namespace and the network namespace. So the user namespace essentially allows you to execute programs as another user, and this means root. So we are actually going to leverage the user namespace to map to root, so we get root permissions. And like I mentioned before, these are all essential to containers. Like, this is the underlying technology for containers. So user namespace, we're going to map our user to root. It's going to give us every single capability. Network namespace, so if you recall from the previous slide, we need to cap net admin. Well, we will get that from the user namespace, but network namespaces are needed to actually needed to do various networky things within your computer without affecting the host system. So network namespaces is like sandboxing networks on your system. So if you can think of Docker networks, that's basically what that is right there. It's your own separate network with your own virtual interfaces, or even sometimes physical interfaces you can pass on through. But it's all virtual interfaces where you can talk to your other containers, and that's how you can talk to them through the host, et cetera, et cetera. It's all set up through network namespaces. So we're going to use a tool called unshare to we're going to use a tool called unshare to actually to create this container and to actually get in there and perform the exploit. So but before we get started with that, the ID command. So before I'm executing this, I'm just trying to clarify here that yes, my name is Fred. I'm the GID Fred. Blah 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 Fred. Right? That's what this process and ID is under at the moment. And if I do a grep cap effect, so effective caps are essentially a process's capabilities that tell the process what it can or cannot do from a kernel perspective. So in this case, the proc file system self status means for this terminal session, get me the status of it, and I'm trying to grep for the effective capabilities. My computer thinks that I can't do anything. We're going to change that. So with unshare, it's a tool, but also a syscall that you can use on the terminal. In this case, we're going to pass in the flags map root user. So this implies a user namespace, and we're going to map my user to root, or I should say root to my user. And I'll explain that in a little bit. And we're going to create a new net namespace. So the moment I run this on this machine, now when I perform ID, I am now root. And if I look at the cap effective, I now have every permission that root would have in this namespace. But there's a couple of zeros in there. Do those really mean anything? The answer is no. Those are just reserve bits. So when I use a tool called capsh or capsh, we can actually decode the capabilities and get a list of what's all there. And in this case, I've highlighted capnet admin and capsysadmin. These are the two critical capabilities we need. We know from earlier that we need capnet admin, but we also need sysadmin because traffic control and other networking tools still require system permissions to run. So this is so when I say that we're mapping root user to my user, this is kind of what I mean. So when I try to read the output of this process's UID map, we get this information 0, 1000, and 1. So basically what this means, and it's not really user friendly, I know, but basically what this means is we're saying we're mapping the root user to the user 1000. In this case, 1000 is me, and it's happening one time. At the end of the day, capabilities and file permissions are two separate things. So even though I'm in this user namespace and I'm trying to use root to perform some sort of action within the kernel, that doesn't mean I have file permissions. So if I try to add myself to Etsy sudoers, that just doesn't work because at the end of the day, my user just doesn't have those permissions. So there are some limitations to user namespaces, and this is well intentional because user namespaces are meant to be used for sandboxing, just like with your containers. And then to actually get out of our container, we just do exit. So this can all be ran through your terminal command line, by the way. So feel free to follow along, but don't follow along too well. This is it. This is the actual exploit in all of its glory. We talked a little bit about assigning variables, getting the path to the traffic control. Here in this case, the only thing I'm really doing different is I'm telling the unshare program to launch bash, and then we're going to give it a file to execute immediately when we enter into the container. This is your entry point in Docker, by the way. So the moment this container executes, it's going to set -x basically just means it's going to list out all the commands one after another, basically kind of just echo them out as they're being executed. It's going to perform the exploit, and then it's not even going to get to set +x. Your computer's toast at that point. Toasted it is. So kernel null pointer dereference. Once again, we now have a scary stack trace, except this time, I didn't really show it in the previous slide, but this time I'm highlighting the actual stack trace here. So the interesting thing about this particular bug in the kernel is that this is happening way after the fact. So this is happening right on ping. So when you execute ping, this is what happens. It performs a send to syscall. It does some magic around the packet, and then it starts queuing it up to be transmitted across the wire, and then we hit the HTTP and queue. So if you recall earlier, I set up the hierarchical token bucket traffic control discipline. It's hitting that, it's going into that function, hitting the exact point where the null pointer dereference is happening, and then crashing the computer. And we can actually confirm this by looking at the top where it says com ping. So we know that the ping command is actually doing this. But isn't that kind of weird, right? Like, why is ping crashing my computer? If you were to see this, if you were to actually look at this as a normal user, you'd be like, how does ping do this? Why does that happen? Well, we can actually fix this issue by first decoding the stack trace to actually find out what's going on. So I want to caution that not every Linux distribution may already have this in here, so I included some extra commands. So essentially what we're doing here is, I should say that every kernel has a script called decode stack trace.sh where you pass it the kernel image, and you can std in or pipe in your input, your crash report, and then output back out your crash report is decoded. Now this is just a small snippet of it, right? And typically on Debian computers, you may already have the Linux source code installed on your computer, in which case, you can use these commands at the bottom of the screen to actually get that. Otherwise, you may have to install it. Sometimes the Linux source uname may or may not work depending on your kernel. But at the end of the day, it produces this detail stack trace that tells us exactly where this crash is happening at. And we can kind of see this whole flow. We have the socket files, we have the IP files, we have the device files, and then ultimately the scheduler file, in which case on line 635, we see this. Now, when I look at this, I think, okay, it makes sense why Q and Q wasn't in that stack trace, because right here, what we're looking at is actually an inline function. So essentially, what's happening here is when we reach this condition, we're getting the return code back from this enqueuing function, and then we're doing something if it worked or didn't. And in this case, this is what that actually looks like. So we have static inline int, qdisk enqueue. So this is the actual function that is performing the crash, specifically on line 806. But to me, this seems like an obvious fix, right? We can just put in if not sketch and queue. So if we recall earlier, functions have addresses. So in C, you can actually assign an address to a variable and then execute it later. This is not dissimilar to, say, in Java or Python, PHP, what have you, where you just pass in a variable into a function and call it later. Even JavaScript, same thing. So you can actually pass in a function. You can actually assign functions addresses to other pieces of code to actually execute it. So here, I'm just checking to see if enqueue is null. If it is, go ahead and enval. Now, I've already alluded to this, but does anyone here can anyone here explain to me why I call this the obvious fix? No? All right, yeah, let's. Okay. Mm-hmm.
But I'm not going to be able to go any further than that because this is 6 levels geekier than I am.
For those who didn't hear in the audience, this is 6 levels geekier than the audience member. I feel that. It definitely is. Any other takers? Any other ideas why this is the obvious fix and not the right one? Yes.
Well, it was a null pointer, it would be 0. So not a 0 is just return an error, right?
So that's exactly what we're doing. We're returning an error when it's 0, right? So 0 is falsy. So if false, return enval, or if not false, return enval, right? Okay. The audience member says I should tell him. Okay, well, the reason why that's the obvious fix is because that I already alluded to it earlier that the crash was happening at ping. Ping is far too late, right? Like, what are you going to do? You as the user, you run ping, you get the crash. What information can you derive from that actually points at the crux of the problem? So no, I actually took a different route. So for this actual fix, I had to launch a debugger, and I painstakingly, basically line by line, went through all the code, all the executions to find this very optimal spot where we can actually trigger an error message from the traffic control side. So when you as the user are typing in the commands, it'll actually tell you, hey, you cannot assign noqueue to a class. Now what's funny, what was particularly funny about this fix is that in the actual documentation for traffic control, they explicitly call out that you are not allowed to assign noqueue to a classful queue discipline, which in this case is what we did. So even kernel developers don't do input validation. Yeah, I'm looking at you guys. Yeah, I know. We all do it. So going back to earlier when we were talking about addresses, in this case, the new ops, we were checking to see if this function has the address of noqueue. So the function that is actually performing the noqueue operation is noqueue_disk ops. So what we're doing is we're actually checking to see that if the address of this field ops is equal to the address of the noqueue function, go ahead and return an error and let the user know that, hey, yeah, you cannot assign noqueue to a class. Now, going into the details and the nitty-gritty of this is like I've been told several times by people way over my head, right? If you really want to know, I did include a link to this blog post where I actually detailed exactly what happens within traffic control to actually lead to that actually leads to this problem. And then I also included a link at the top to the actual kernel patch that I submitted to actually fix the problem. And yes, this vulnerability has been around since 2015. There are more. All right, so now that we know that it's safely fixed, let's actually talk about some mitigations. Keep your kernel updated. I know it seems obvious, but you'd be surprised. Going for that 100% uptime is not great. What you're really doing is you're opening yourself up to vulnerabilities, and if you're really going for 100%, like that implies to me that you don't have a disaster recovery plan. So, yeah, my code's coming after you. Operating kernel is actually pretty safe, unlike a lot of user space software, which user space meaning anything that the user would actually run on your systems. Whenever that updates, you have many hands working on them. Same thing with the kernel, but bugs are always introduced all the time, and fixes are always rolled out. Blah 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 blah. But they often break more so than the kernel. Kernel is actually pretty well tested. Every update to a minor patch actually includes many vulnerability fixes and many other fixes to the kernel to actually make it more stable. Now, there was that one time, maybe several, but there was that one time this year where it did cause some corruption on your disk. However, that was promptly fixed, and then a new version was promptly released. But the important thing to remember is that upgrading the kernel is like relatively safe. Now, if you try to go to major releases, in this case jumping from 5.15 to say 6.1, there's going to be a lot more features added to the kernel. So the way the patching system kind of works is anything represented in Z here on this slide essentially means that no new features are introduced in the kernel. Sometimes new features are introduced because of patch backporting, but most of the time that Z represents no new features. Anything meaning from 5.15 to 6.1 or 6.6, new features are introduced. So at that point, you may want to actually test your kernels. And please, do update. There's more harmful people out there than me. Okay, locking down user namespaces. So this is a little tricky. I don't expect everyone here in the audience to go home tonight and to actually implement these things. This is more of an example of what could be done to address these issues. First and foremost, so I put this list in order of probably best to like least preferable way to lock down user namespaces, because I want you to keep in mind that user namespaces are still very important for actually sandboxing applications and tools. It just so happens that the kernel is buggy. So the first thing I like to talk about is what's called an SE Linux policy. SE Linux is a security subsystem for Linux that does just that. It does security for Linux. You can program rules for it to say, like, certain programs can do certain things. And in this case, you would allow, in this case, dom a underscore t to dom a underscore t user namespace create. You'd allow that program or something to create user namespaces. That feature did not exist in the kernel prior to 2022. I actually added that in myself. So this is the latest and greatest in namespace security. Next, we can actually try to control the number of user namespaces we can create. All your systems that have user namespace enabled has a sysctl command that you can call, where you can assign the number of clones a certain process can make. This one is a little tricky to explain, because when you think about normal program execution, there's several ways you can do it. If you're talking about from from a user executing it, that would just be you, the user, typing in the command and executing the program. But systemd could also execute a program. Now, systemd is your most likely your system's init system, which is kind of control of your entire operating system. You can think of systemd as your operating system in a lot of cases, and that can execute programs, right? So really, the intent behind this this specific command here to control the number of user namespaces is such that if you're going to fork a process, by fork I mean create a new one from the parent, so create children, you can use this to say that any process below this one can only create so many user namespaces or none at all, right? So you would use this as a means to whenever you're about to perform some sort of operation, you can clone it, which is another way of saying fork, create threads, etc. Or you can fork it and then set how many user namespaces the underlying processes can make. Going down the list. That one's kind of weird because it's a tree. But going down the list, we have you can disable namespaces altogether. This actually is only introduced in a few operating systems. The only one I know of at the moment is Debian, so the one I'm running on this computer right here. If I wanted to, I can completely disable user namespaces and just be done with it. For anyone else who wants to completely disable them, you're going to have to compile your own kernel. This comes by default. So you just disable that config option. But it gets a little weirder. So seccomp. This is probably something just like with user namespaces, probably no one here has ever heard of. If you have heard of it, you're awesome because you know what's up. So seccomp is essentially a tooling to allow you to control syscalls on your system. So syscalls are the mechanism in which your programs communicate with the kernel. So whenever you open up a file, that's a syscall. Whenever you write to a file, that's a syscall. Basically, if you ever want to do anything useful with your computer, you're creating syscalls. Now, seccomp is a way for you to say, when I, again, clone or fork a process, anything underneath that in the child cannot perform certain syscalls. So if you want to create a program that cannot open up any file whatsoever, you can use seccomp to do that. Now, the interesting thing about seccomp is that there is a command line tool you can run to actually to execute programs with seccomp with an easy way to configure it. Of course, created by Cloudflare, but I didn't include that in the slides. But that does exist. But traditionally, seccomp, you would actually program this into your Python, PHP, maybe PHP, I don't even know, whatever, into your actual programs itself to actually prevent syscalls being run from underneath them. So Docker actually comes with a pretty comprehensive seccomp policy. We'll touch up on this a little bit later when I demo, but essentially, Docker makes it so that I cannot run my exploit. Again, we'll talk about it later. Kubernetes also has comprehensive seccomp policy, but because Docker has it, of course Kubernetes have it. And for those who are not familiar with Kubernetes, a great way to think about it is just a way to create many machines and all with containers, and they do fun things. Ryan over here has a better explanation. I don't got it. Don't run scripts from the internet. We all do it. I do it. You do it. You do it. You do it. Some of you do it. I know, it's crazy, right? Right? That we do execute scripts, right? Like it's wild. Just be careful out there. That next script might be mine. Okay. My computer actually is set up to take a while to reboot because I have it set up that whenever I crash it, it will generate a comprehensive crash report and crash dump for me. So I will answer questions while this computer reboots. Until then, we are actually going to look at how we can crash this computer with Docker. going to be awkward holding the microphone and doing this, but I'll try to do this with one hand. So I created a repository. I will, of course, upload this at the end of the talk. I have this has everything I've used in the presentation. I have a kernel that will download and compile and install so you can actually toy with it. I have container stuff that will create the Docker container, execute the Docker container. I have the small little C program I demonstrated at the very beginning, and then of course a kernel module that will crash a kernel. Do keep in mind there are dependencies to install for all these things. I just didn't include them necessarily in the README. I think I did. Yeah. Yeah, I listed a lot of things here. Right? Yeah, virtme, yeah, libbpf tools, which, comes with the capable, yeah, all that other stuff. Okay, cool. Q. Okay, so back to the container. So I'm going to look at the container. Okay. We forgot to turn off Docker. 1 second. I said Docker, I meant Discord. Let's see, F9, not that one. Can you send it again, Ryan? Did you send it again? No, go ahead, send it again. I just want to make sure it's done. Yeah, everyone DM me. Okay, I'm pretty sure it's done. My bad. It all happens. Okay, so where was I? So I'm going to show what the container actually looks like. So container makefile. Okay, so just to show that I'm not like totally crazy here, when we execute this, we will build a Docker image and then we will execute it. Now, the interesting thing is at the very bottom of this, when I run the container run makefile target, you'll notice that I'm passing in cap add net admin. Now, there was a presentation sometime this year about Docker, and during that presentation, there were some mentions that maybe you couldn't really do much networking with them. Actually, you can, and the reason why this works is because with the traditionally, when you run the Docker daemon on your system, it's usually ran as root, and you can also tell Docker to run as your user, which a lot in the instructions which says you can or you should or shouldn't really do. But I mean, when we're all running Docker on our personal computers, we don't really care, right? But so in this case, because the Docker daemon is running at root, I can tell Docker to go ahead and give it the cap net admin. Now, in a lot of cases, this might be fine because a lot of people do write containers that actually do networking things. Notably at networking companies, to be a little bit more specific. So it's not uncommon to kind of see this, and you can actually set this capability through a Docker compose file as well. So you don't necessarily have to run the actual Docker command to run this image. And when we look at the actual image, let's see. Container and Docker file. It's pretty simple. I only install a few dependencies here. I could have created an image based off of Debian that already included all these, and all I had to do is just run the actual exploit. But it's fairly simple, and the exploit is going to look a little different. Oh boy, capital letters. Container and exploit. Okay, so it looks very similar, but it's also a little bit different. Notice how we're not using the new user namespace. Well, as mentioned before with the actual Docker run command, we don't need to in this case. In fact, Docker actually in their seccomp policy actually forbids unshare. So there is some protection that you get with Docker. It's just too bad that in this case we're going to ignore that. All right, you guys ready? All right, it's going to be very exciting. Oh, there's not going to be any sound. It's quite silent. That's it? No, literally, that's it. Questions? Yes, you.
What I'm gathering, this is all the result of programming. Oh, yeah.
Okay, there we go.
All right. By my understanding, this is all the result of a programming error with the null dereference, correct?
Yep, that's exactly it.
I also understand that the Linux kernel is starting a project, a push to move things towards Rust, where that would be considered an unsafe operation. Do you think, in your capacity as a kernel developer, with your experience, that that would help mitigate these type of vulnerabilities?
It's kind of hard to say. When you're working with in the actual kernel, you're actually working fairly close to bare metal. Now Rust is fantastic for memory safety and things of that nature. But the current I don't follow the project too closely, but at the current moment, the best case for Rust at the moment is just drivers in general. But when you're interfacing with actual hardware, you could still run into a case where you access invalid memory and crash your computer. So it can happen. Yeah.
Thank you.
I've got a question. Did you crash the Docker container or your actual host
Actual
system?
laptop.
Interesting. Why are we not getting like a blank screen right now?
Because
Because it just is going to display what the last thing it was displayed.
I mean, yeah, that's essentially it.
I had that whole demo with the camera set up to show you all, but didn't even need it.
Well, I mean, no, it's gonna reboot here in a minute. I mean,
Okay,
again,
let me
it
switch
takes
to
a
it then.
while.
Okay, hopefully we'll see something cool happen there in a minute.
Because just to prove this point that it's actually crashed, see how I'm running ping? Why aren't we seeing any results?
True.
True. I was going to give a presentation. I was going to demo of Kubernetes. I was going to set up a nice little website. I was going to say like, oh, here's my fun little website, and then I was going to upload a new YAML file that's going to run this random image I found off the internet. But I decided that just running Docker itself would kind of shows the point that when you run this, you can from Kubernetes, from Docker, or whatever, you can crash machines. Yeah. And that's why I got a 5.5 out of 10.
Why not higher?
Good question. Why not higher? It's mitigatable. If this was remote code, I would be in the news.
Any other
Just like
questions?
CrowdStrike.
Any other questions?
Will you walk through okay, I'm going to pick up this bug and poke into it, and what made you just keep going on it, and kind of the human part of it, how long that took, and all that?
I made it look easy tonight. It was not easy. The challenge, the main, yeah. So it was a fairly long process. I mean, once I was assigned the bug, it was very quick turnaround, I would say. But it still took like a lot of research because I had to understand exactly what traffic control was, how it worked, how queue disciplines worked, why this specific combination of commands like come together and actually produce this exploit. On top of that, I had to figure out. Yeah, I could crash with root, but how do I actually, make this unprivileged? I showed you how I did it tonight, but at the time it wasn't so obvious because, I talked a little bit. See, now it's rebooting. So I talked a little bit about the case of where. Oh, great! I'm losing my train of thought. I guess just to take a step back. When it came to debugging this thing, it was definitely just a lot of going through line by line of source code, going through GDB, running through all the things, trying to figure out which combination of all these things made it work, and then when it came to root and making unprivileged, I think the defining moment for us as a team was the fact that we were able to do this with virtual addresses or virtual interfaces and not physical interfaces. Now, I was informed that you could pass over physical interfaces into your containers, but I can't zoom in the text. Sorry, but um, but the aha moment was the fact that it was a virtual interface, and if you could, and because we knew that containers like really heavily rely on virtual interfaces, it just seemed like a very logical conclusion at that point. Again, it was not there was a lot of debugging, a lot of testing, a lot of research, a lot of writing. When you look at the blog post, again, I've told people way over my head, right? That's because of the research. There's a lot to it. I dumbed it down tonight. I don't mean to it's just not good for a presentation if I go too thick into the weeds, so.
So what does the process look like once you find an issue like this to actually reporting it, getting it fixed? How does it get disclosed? How does other companies and organizations learn about it to patch it? What's that look like?
It's pretty boring. You go to his website and you basically you type in you give the we went to the I think it was the MWrite website. You go in there, you submit a vulnerability, right? You give a description of what it is. Maybe you give like an actual example of what the exploit is, and then eventually you'll get assigned a number. Now, once you have a number, at that point, you're not supposed to disclose it. So the kernel documentation has very strict guidelines on disclosure and how to report these vulnerabilities. That recently changed, but back when I did this, the process was once I found the fix, I submitted a patch in secret to the maintainers. They reviewed the patch. Once they gave the go-ahead, they merged it in secretly. So nobody knew this was actually merged in when it was merged in. And then basically from that point on, I had 30 days to, if I wanted to, I could disclose it. And I did. I disclosed it about, I think it was like mid-January, and I already had the fix in December and early January. Well, okay, the timeline doesn't work out. I don't remember when I did the disclosure. Blog post has the date on it.
Was the more challenging part finding the permissions elevation that made this problem possible, or tracing the null dereference once you figured out what general area it was part of?
Finding where the null reference was trivial. As we could see from the stack trace earlier in the presentation, it was fairly simple to find where that was. The challenge was finding out where. The challenge was not doing the obvious fix. The permissions was also not a huge deal too, because we're already familiar with working with network namespaces and user namespaces, so that was not an issue either. It was all the crux of the work was figuring out exactly how traffic control worked. that was the hard part. Yeah.
What was the most interesting part for you in this process, and why?
What was the most interesting part of this process? Definitely the debugging part of it. You have to be a real nerd to want to go deep and try to figure out exactly how things work under the hood. But I definitely want to say that the most exciting moment I had was when we were able to successfully crash a few things that we weren't supposed to. I can't say anything about that, but that was probably the more exciting part. Just the thrill of doing naughty things. But other than that, it was definitely the exploration of the bug and figuring out how exactly it worked, why it worked. I've already said that before, but that's the gist of it. Yeah.
Okay, I think that's it. Let's give Fred another huge round of applause.